Okay, so just going into this idea of photons of light, we're just going to do a very, very quick reminder of what actually, what is light, how we looked at light in the past and how do we consider different types of light really. And you may remember that we've got something called the electromagnetic spectrum, which if you've done, if you've been through GCSE, you will know that this starts with radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. And we will generally say that if you were to imagine visible light here, okay, it has a certain wavelength, a certain frequency. Usually we say that at the red side of visible light, you're around about 700 nanometers of wavelength. And at the violet side, you're going to be at around 400 nanometers of wavelength. And then if you go longer wavelength, you go towards the radio wave part of the spectrum. If you go shorter wavelength or higher frequency, you come towards the gamma ray part of the spectrum, okay? But this is all, like we said, this is all talking about waves. This is all talking about wavelength and frequency and things like that. When we're talking about the photon model, we want to talk about individual particles of light that have a certain amount of energy. And what we would say is we would say that a individual light photon over here somewhere would have a far lower energy than an individual light photon over here somewhere, okay? And there is an actual calculation that we can do. And it's a fairly straightforward one, because what we generally say is that we can see that as the frequency increases to high frequency here, the energy increases. And we would actually say that the energy is proportional to the frequency of the light, okay? Now, when we have an equation like this, we can always say, if we've got a proportionality, we can always say that the energy is equal to some constant times by the frequency. And in the case of light, this constant is something called the Planck constant. So finally, we say that energy is equal to the Planck constant, which we give the letter h, times by the frequency. Now, just on this point here, we also know that frequency is the speed of light, which we use the letter c, divided by the wavelength. So just our standard wave speed equation here, frequency is speed divided by wavelength. So we also know that the energy is equal to hc over lambda. So here we have the two equations. They are both exactly the same equation. We've just got h multiplied by frequency or h multiplied by the speed over the wavelength. It's just if you want the equation in terms of frequency or wavelength. Now these two equations are absolutely crucial and you're going to use them all the time as we go through. But what is this constant here? Okay, so this Planck constant is an extremely small number. It's pretty much the smallest, well, it is the smallest number that you're going to be using in A level, okay? And this Planck's constant is given by the number 6.63 times by 10 to the minus 34, okay? And as a side point here, something you could have a go at is you could have a go at trying to work out what the units of Planck's constant are going to be, using our knowledge about energy in joules, frequency, etc. So work out what the units are going to be, okay? I will, if you want to pause it, you can do that now, because I'm going to have a go and show us how that will be done. Okay, so let's have a look at a simple example of how we are going to use this equation to work out how much energy a photon of light, an individual particle of light, has. We'll do the two extremes of visible light. So we'll go for red light, and then we'll go for violet light, and then we'll maybe look at an example of somewhere in the gamma part of the spectrum. Okay, so let's look at violet light. Okay, so the highest frequency or shortest wavelength part of the visible light spectrum. So violet light has a short wavelength, and it's something along the lines of 400 nanometers, which is 4 times by 10 to the minus 7 meters. So if we put this into our calculation, we're just going to say the energy of one photon of violet light is equal to h times by c over lambda, which is 6.63 times by 10 to the minus 34 times by 3 times by 10 to the 8, and we're going to put that all over 4 times by 10 to the minus 7. Okay, so if I do this on the calculator, 4.97 times by 10 to the minus 19 joules. Okay, now this is a very small amount of energy, and you would expect that from a very, very, very small particle. A single particle of light, okay, it's going to have a very small amount of energy. Now, this is also probably in a unit that is not going to be particularly useful for like thinking about, like when you're thinking about numbers. A number like this, it doesn't really mean very much to us, okay? So we can probably come up with a better unit than the joule. Now, in a previous lesson, in another lesson that I've done on here on this channel, aimed towards GCSE, I looked at something called the kilowatt hour. And a kilowatt hour is a different unit for energy on a larger scale. So when you're using an oven, for example, and it's got 5,000 watts, 5 kilowatts, okay, and you're using it for a couple of hours, you're gonna have millions of joules of energy, okay? And 10 million joules of energy is a large number. We don't really want to think in terms of those numbers. So we use a big unit so we can deal in smaller numbers. And that's how the kilowatt hour works. The electron volt is something very, very similar, and the electron volt is something that is a unit that we're going to use for small amounts of energy. Okay, I'm going to show you how it comes about and what it really means. So, now, if you think back to electricity, you'll remember the equation: work done or energy equals the charge multiplied by the potential difference or the voltage. Okay, W equals QV. Now, if we think about this in terms of our sort of standard units, we would generally say that if you had 1 coulomb of charge and that coulomb of charge kind of potential difference of 1 volt, you would have 1 joule of energy. Okay. Now, what we do is we say that we're going to use a much smaller amount of charge here. We can say rather than having 1 coulomb of charge, which we know to be about 6 times 10 to the 18 electrons, we're going to say we have 1 electron. Okay, we're going to say how much energy would be needed to accelerate or how much energy would a single electron gain if it accelerated across a potential difference of 1 volt. Okay, so we're going to say 1 electron, so I'm going to write it in words here, so 1 electron, and we're going to say 1 volt, don't know what that D, 1 electron and 1 volt here, so we're going to put this in coulombs now, and if you take that, okay, 1 electron multiplied by 1 volt, you get something that is very imaginatively named. You get 1 electron volt. Okay, and this is a unit. Now, how much energy is 1 electron volt in joules? Well, we can do that calculation as well. We can say 1 electron has a charge of, we're going to go back to our coulombs volts, because if we do coulombs times volts, we get joules. If we do electrons times volts, we get electron volts. So 1 coulomb, 1 electron in coulombs we know to be 1.6 times by 10 to the minus 19 coulombs multiplied by 1 volt. It's a very easy calculation. It's going to give us 1.6 times by 10 to the minus 19 joules. Okay, coulombs times volts gives us joules. Okay, so 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. That is all we have to do when we're thinking about electron volts, is we just think of it in exactly the same way that you would think of kilowatt hours. It is just a unit of energy, but it is a different scale, okay? Just like miles or millimeters are different units of distance, the electron volt and the joule are just different sized units for energy. So when we come back down to this number here, we can work out how many electron volts that is, and we are going to divide by 1.6 times 10 to the minus 19. Okay, if you ever get into a point where you're struggling to remember, is it times or is it divide, what I generally say is you can think of it, just think of both. Okay, so times it, if I times this by 1.6 times 10 to the minus 19, I'm going to get you put it into your calculator and try it, but you're going to get an extremely small number. Okay, it's going to be 10 to the minus 40 or something close to that. Okay, so if you divide this number by 1.6 times 10 to the minus 19, you're going to get a number on a normal scale, 3 or 4 or something. Okay, and this is what we're looking for here in this situation. Okay, because if you've got a small unit, you're going to have a reasonable number of them. So this divided by that, if we just throw my calculator on the floor, it's still on. Okay, so 4.97 times 10 to the minus 19 divided by 1.6 times 10 to the minus 19 is going to give me 3.1. 3.1 electron volts. Okay, so the energy of a single photon of light is either for violet light, okay, which is 400 nanometers, is about 5 times 10 to the minus 19 joules, or about 3.1 electron volts. Now I'll do one other example of this. We're going to run all the way through, and I'm going to say I'll write a question here on the board. Okay. Right. So in this question, I've actually worded it in such a way that we've considered gamma rays and also photons. So I'm going to read the question. A gamma source has a power of 4 milliwatts. I don't know how realistic this is, if this is particularly powerful or not. A gamma source has a power of 4 milliwatts. The gamma rays emitted have a wavelength of 1.5 times 10 to the minus 15 meters. Calculate the number of photons emitted per second. Okay, so I've referenced rays, which kind of means waves here, and I've also referenced photons. Okay, now what I'm going to have to do here is I'm going to have to initially calculate the energy of each photon of this gamma, of each one of these gamma photons, and then I'm going to work out how many of those make up 4 millijoules, because if effectively when I've got a question in watts power, it's joules per second, isn't it? So the per second means that we're looking at this in terms of 4 millijoules. So let's do this step by step. So first of all, I'm going to say the energy of each gamma photon. E equals h times by, we've got wavelength, so I'm going to go c over lambda, which is 6.63 times by 10 to the minus 34 times by, I don't know if we see on this edge of the board, 3 times by 10 to the 8, all over 1.5 times by 10 to the minus 15. We'll work this out. We've got fraction 6.63 times 10 to the minus 34 times by 3 times 10 to the 8 over 1.5 times 10 to the minus 15, 1.326 times 10 to the minus 10. 1.326 times by 10 to the minus 10. Out of interest here, we don't need it for this particular question because watts is a standard unit, so I'm gonna keep this in joules. But just out of interest, let's see what that is in terms of electron volts as a side note here. Oh, it's not giving me standard form. What were we saying here? 1, 2, 3, 4, 5, 6, 7, 8. So this is about 8.3. This would be 8.3 times by 10 to the 8 electron volts. So that's what, 830 mega electron volts, which is quite a high energy gamma ray here. Now, so now we've got this amount of energy here for our each individual photon. We can simply work out how many of these are going to go into this. Okay, so we're going to say that we've got 4 times by 10 to the minus 3 joules per second, 4 times 10 to the minus 3 watts, and if we divide that by our 1.326 times by 10 to the minus 10 joules, we will get 4 times 10 to the minus 3 over 1.326 times 10 to the minus 10. We get, again, not standard form, 1, 2, 3, 4, 5, 6, 7. We get about 3 times by 10 to the 7, and our units here would be seconds to minus 1. Okay, so we get about 3 times 10 to the 7, so about 30 million photons per second. Okay, simple as that.